How does a turntable produce its distinctive vinyl sound? What delivers an outboard motor's 300 horsepower and its hairpin twists and turns? And how can a 1-meter treadmill deliver a tougher workout than a 10K run? To answer these mysteries, we dive deep inside these and other extraordinary machines to reveal the secrets of how things work. The turntable. For the committed music lover, nothing beats a vinyl record sound. So can this 21st century version of old-school technology sound better than digital downloads? 240 precision-built parts work in unison. 2 interlocking zinc alloy spinning platters are perfectly balanced for maximum stability. An ultra-tough diamond-tipped stylus glides through the vinyl's 1/2 kilometer long groove. An optical sensor ensures the motor spins the turntable with pinpoint accuracy at 33 1/3 revolutions per minute. These components combine to produce the ultimate sound experience. The turntable recreates the magic of the recording studio in the front room. But records suffer from one tune-destroying drawback. They skip. The secret to a stylus that never bounces lies in the way that workers in this Scottish factory build the arm that holds it.
It's a precise process, and you have to take your time and care.
Graham's job is to hand-build the arm.
If it's assembled correctly, then it will follow the groove properly and pick up the information that's in the groove.
The arm must guide the stylus as it rides the record's groove. So Graham fits 2 bearings into position. One bearing lets the arm pivot up and down, the other lets it swing from left to right.
The bearings will allow the tone arm to move smoothly up and down the actual arm assembly itself, so the head and the stylus can follow the groove more accurately.
Graham tightens a nut to stiffen the bearing. This way, the arm swings just enough for the stylus to travel down the record's groove smoothly.
The arm should swing between 80 and 100 times from side to side. It's swinging slightly more than I would like, so I'm going to have to try and adjust it very, very slightly.
Graham tweaks the bearing's tightness and sets the arm off again.
It's a very fine line between having the arm achieve the correct number of swings and dropping below that level. That's looking not too bad.
Graham then uses a stethoscope to check the arm swings in absolute silence.
I'm listening for a small tapping noise. If we don't hear any noise, the bearings are well adjusted and moving correctly. This one sounds good.
The stylus follows the record's groove with extreme precision. But what transforms the tiny bumps and valleys on the plastic into music? A pure carbon stylus navigates the tiny fluctuations in the vinyl's groove. The stylus sits on the end of a cantilevered arm that vibrates a super-light miniature copper coil back and forth. As the coil moves between 2 magnets, it generates an electric current. The current drives a mini amplifier and both of the speakers to create that classic vinyl sound. The stylus can reproduce music exactly as it is played in the studio. That's as long as the record spins at a constant speed without any wobbles. The secret to keeping the turntable's platter spinning straight is the way that workers put it together.
The inner platter is a casting that's been machined to very high tolerance using diamond tools to get a very good finish. The spindle is press-fitted into that part.
David works as an audio development engineer. His goal is perfect sound reproduction. The platter is made from zinc alloy. Computer-controlled diamond-tipped tools create its precision finish. The spindle must be in the dead center of the platter. If it isn't, the platter will wobble as it spins.
We're going to be measuring the flatness of the inner platter to make sure that it will remain flat and not give a huge wobble, which would give us speed instability. If we change the speed, the pitch of an instrument on the vinyl will change. If it's unstable and it's wavering, then you will hear that note waver.
A sprung dial records how much a needle moves up and down as the platter spins.
So we get it touching, and then give this a bit of a spin. So the fact that we're within 0.01 of a millimeter shows you how little it's actually moving on that surface as it's rotating. So we're good to use that part.
Workers build the turntable to spin flat. But as music booms out from the speakers, the vibrations can rattle the record and distort its sound. So engineers construct the turntable in an ingenious way. A stainless steel plate that holds the motor attaches to a super-rigid 2mm thick aluminium platform. 3 tightly wound springs act as shock absorbers to isolate the turntable from vibration. The zinc alloy platter rotates on a lubricated single point bearing to cut friction as it spins. So even dancing feet won't make this record jump as it plays uninterrupted music the whole night through. A wobble on the platter isn't the only way the deck can spin at the wrong speed. The motor can miss a beat too. The key to the turntable's constant speed is the way that workers assemble its electronics. Gordon builds the circuit boards that drive the turntable speed sensor.
Without the circuit board, individual components within the product won't know how to talk to each other.
If the electronics get the timing wrong, your favorite music will be horribly out of tune.
On this side, you can see an optical sensor. This optical sensor will measure the speed that the turntable is turning at.
The optical sensor monitors the progress of a mark on the platter edge. The sensor keeps the platter spinning at 33 1/3 times per minute.
The optical sensor measures the time it takes that mark to come around, thereby calculating the speed that the turntable is turning at. The speed will be changed accordingly to keep the speed of the turntable and the platter constant.
Gordon's special printing machine builds up the circuit board resistor by resistor.
Each one of those little brown specks that you can see there is an individual capacitor.
The machine installs over 40 components a minute. It positions all 600 components onto the circuit board in a quarter of an hour.
So this is the printed circuit board before it's been populated with all the components, and this is the fully populated circuit board itself, complete.
Workers hand-build each turntable so these smart design innovations can perform to the max. Thanks to the dedication of the craftsmen and engineers who make these turntables, they produce a sound that rivals anything the digital age has to offer. The Treadmill. It helps millions jog their way to a healthy body. How does the running belt replicate the road so runners can pound out the kilometers? Wrapped in a heavy-duty steel frame, over 500 parts work together. A powerful touchscreen computer control unit sets the pace. A heavy-duty electric motor spins 75 times a second to power the deck for over 90,000 kilometers. A double-layered non-slip rubber and woven fabric belt cuts friction for a smooth run. It's a motorized running track to match your pace kilometer after kilometer. The treadmill can run day and night for over 14,000 hours straight. How does it keep going while an 80-kilo runner pounds on the track? The key to the treadmill's endurance is the way that workers in this Washington State factory build its sturdy frame.
The machine is going to be working 24 hours a day, pretty much. It's not going to stop.
Alex mans the robot that welds the frame together. He mounts 34 pieces of steel onto the jig and then sets the robot to work. The robot is fast and accurate and completes 140 welds in 5 minutes. But there are some welds that Alex can only reach by hand.
Wipe your eyes. These welds is not going to break. This is not going to happen.
The treadmill's frame is strong, but the running deck must also be ultra stable to give a comfortable workout. The belt glides around 2 finely balanced 12-kilogram steel rollers. These run on 4 bearings to keep it rock steady. 6 rubber bumpers attached to the base act as shock absorbers as each foot pounds the belt. Inside the deck is a 2.5 centimeter thick board coated with wax. It's mounted on a hinge at one end and gives a solid surface for your foot to push off. This makes it easier on your joints, even if you're training for a marathon. The belt that turns around the board must run super smooth to stop jolts to the runner's stride. The key to the belt's smooth action is the way workers balance the machine's moving parts.
If the roller was imbalanced and it got put on a treadmill, what would happen is the treadmill would literally vibrate to the point where the treadmill could actually move.
It's Mark's job to make sure that the treadmill's rollers run vibration-free.
What we want is everything to be smooth like glass, just no vibration, runs smooth, and just glides right along.
He uses a computer-controlled lathe to shape the cylinders perfectly. Then Mark checks the machine's work.
We're gonna go ahead and spin her up.
He spins the roller to make sure its weight is distributed evenly.
Right now, the computer's measuring the movement that's happening from the roller tube. When the computer tells us what angle and how much weight to correct for, we rotate to that angle, and then we go ahead and add weights to eliminate that imbalance.
Mark cuts out strips of metal weights and sticks them to the roller's inner surface.
And what we can do is literally just press these on. So once we've made the correction to our part, we go ahead and run it up again. And we have a good part.
This roller is perfectly balanced. Now it must run at just the right speed. The rollers must spin harder every time the runner's foot hits the belt to counter the runner's weight. If rollers and belt don't match the runner's pace, they could end up flat on their face. The computerized console sets the desired speed. Each time the heel hits the deck, the belt starts to slow. The drive system compensates for this extra impact. In a microsecond, an electronic controller detects the change of pace. It powers the motor to spin faster. This returns the belt to the selected speed to create a smooth running surface that matches the runner's stride. The treadmill's electronics make for a jolt-free workout. But if the belt runs loose, it could bring the machine to a crashing halt. The secret to a safe run lies in the way workers fit the running belt onto the rollers.
You want to make sure it's straight. It's not going left or right.
Abdullah runs the treadmill final assembly line.
You have to tension the belt. If you leave it loose, then the unit is not going to run.
Abdullah increases the gap between the rollers to even up the tension across the belt. If the tension is out of balance, the belt will slip away to one side.
The belt is tight, and in both sides in same alignment.
Before it's shipped, workers slide the running deck into a test booth where it must pass an inspection.
This is where we test the unit before it go to the customer. We do like 26 units every 2 hours.
Maria's job is to make sure the deck will last the distance in a gym.
That's a very good way to lose some weight.
But she isn't just keeping fit.
I burn in some calories like that.
She's checking Abdullah's work all the way up to the treadmill's maximum speed.
I cannot run that fast. I know maybe some people does, but like myself, I can. It's looking good so far. It's not moving to the side, so it's good.
The deck is good to ship for assembly at the gym. The never-ending treadmill is a precision-engineered calorie-burning machine. Every day in gyms across the world, it keeps millions of people in peak condition. The outdoor grill. Perfect excuse for a family get-together on a hot summer's afternoon. How does this machine create the meat's distinctive char-grilled taste? Inside a heavy-duty steel chassis, 180 parts work together. T-shaped valves deliver the perfect air-gas mix. An electric spark lights the fire. Stainless steel flash tubes feed the lit gas to 4 corrosion-proof burners with tiny holes to spread the flame. On top, 4 stainless steel bars channel this heat evenly to a 30-rod stainless steel cooking grate, which roasts to a searing 200 degrees Celsius. This machine cooks and char grills any meat perfectly. The grill's flames are sensitive beasts. They need a perfect mix of gas and air to burn, and they must be the perfect distance apart to catch light in quick succession. The secret to the burner's rapid ignition lies in the way that workers in this New Jersey factory build them.
There is different holes in the burner. You got the actual burner holes. You got the little air holes on the bottom. They allow the flame to jump from one side to the other side.
It's Jason's job to transform these 6-meter-long steel tubes into highly responsive flamethrowers.
This machine cuts the full-length tubes down to the correct size. It'll just keep feeding until the end of the line.
This automated drill head cuts 28 holes into the burner tubes.
The machine will grab a burner, put it into place, and then it'll carry out the whole process to put all the holes that we need in the burner.
If the holes are too far apart, the flames won't jump across the gap and the grill won't light. If they're too close together, the grill will burn too hot and incinerate the burgers. The automated drill cuts every hole in exactly the right position. It creates a grill that bursts into flames with the very first spark of the ignition. The grill's 4 burners can generate impressive heat, but using high-pressure gas straight from the cylinder would blowtorch the meat rather than cook it. A chef needs complete control of the gas flow to cook meat perfectly. As high-pressure gas rushes into the regulator, It pushes against a rubber diaphragm attached to a valve. As the diaphragm flexes upwards, it snaps the valve shut and blocks the gas flow from the bottle. The rest of the gas escapes along a pipe to the burners, where it mixes with air and burns. As the pressure in the burner tubes drops, the valve opens up and the cycle repeats to create the perfect flow for a constant and even cook. The burners sit at the heart of the grill, inside its frame. The key to the grill's sturdy design is the way that workers shape the metal.
My job here is to create 3D shapes out of cut pieces of metal and pretty much turn them from flat to a finished part.
It's Fabian's job to transform these steel sheets into the grill's casing. The frame begins as three 3.6 square meter sheets of stainless steel. Workers use a 3,500 watt laser cutter to cut the sheets into 24 separate pieces. Fabian then fits the freshly cut pieces into his bending press.
This machine, it's applying pressure to the metal, which will then bend the metal and put it to the shape I needed.
This press applies 5 tons of force. If Fabian positions it incorrectly, the final part won't fit.
Let's say you have 5 bends. After that 5th bend, it will not fit right if I don't get any of this correctly to begin with.
Each part is precision crafted. They don't leave the press until Fabian is sure they make the grade.
Right here, I'm supposed to have a square bend, which would come right up along this line here, and I'm actually a little short.
A couple of tweaks squeeze the part to perfection.
There you can see, I got a nice square bend all the way across. We just try to get it as perfect as possible. It's my job.
Workers then screw the 48 pieces of metal together to assemble the finished grill. Burgers cooking on the grill are one of the great smells of summer. With millions of grills sold worldwide every year, it's a smell to look forward to for many summers to come. The Outboard motor. Its 300 brake horsepower charges this boat through the water at 45 knots. How does this brute of an engine also get the boat to twist and turn? A super light plastic shell wraps around 100 moving parts. Its fuel-injected 2-stroke engine is as powerful as a sports car. A hydraulic-powered trim adjusts the angle of the engine up to 20 degrees to keep the boat perfectly balanced. A stainless steel 35-centimeter propeller spins more than 50 times a second for a fast but smooth ride through even the choppiest waters. The motor must be lightweight and pack a serious punch to thrust the boat forward. The key to the motor's super-efficient power output is the way that workers in this Wisconsin factory, whose founder invented the outboard motor, harness the explosions in its cylinders.
It's high-pressure fire burning in there.
Chris works on the engine assembly line.
The engine blocks are made of aluminum because it's lightweight, it's strong.
Workers cast the engines from aluminium. This cuts their weight and boosts their power efficiency. But there's a problem. The engine's explosions burn at up to 2,000 degrees Celsius, but aluminium melts at 660 degrees. So Chris must slide a cast iron sleeve into each of the 6 cylinders to protect the engine block against the ferocious heat.
The aluminum would melt if you didn't have the sleeves in there. It's really not strong enough to withstand the pressure and the heat of the engine. We push the sleeves into the block with a special machine. Sleeves are in. This block is good to go to machining next.
At full power, the engine's pistons pump up and down inside the cylinder block at an incredible 100 times a second. To stop the engine tearing itself to pieces, workers use a technique called honing. It allows oil to lubricate the lining of the cylinders.
The honing works by going up and down, and the tool turns at the same time. And what it produces is a crosshatch.
Rich machines a pattern of crosshatches into the cylinder linings.
If you magnify that crosshatch, it has peaks and valleys in it, and that's where the oil sits. And that's what keeps the pistons from sticking.
The oil increases lubrication and cuts friction to extend the lifespan of the engine. The explosions in the aluminium engine block produce incredible power. How does the motor time them exactly right? Inside each of the engine's 6 cylinders, an electrically driven hammer forces a spring-loaded valve open. The valve injects the right amount of fuel into the chamber for maximum efficiency. So the pistons turn the crankshaft 6,000 times a minute. This spins the drivetrain to power the propeller. This way, the lightweight motor delivers the power-to-weight ratio of a superbike. The 6 pistons are at the heart of the outboard engine. If the pistons don't pump in unison, they could shake the motor to pieces. The secret to transferring power smoothly between the pistons and propeller is the way that workers put the engine together.
You have to have patience doing this op because it's really critical.
BB assembles the engines by hand. She slides the 6 pistons into the engine block cylinders to begin the assembly.
It's very crucial that you have the pistons installed right and everything is in the right spot.
The pistons deliver power to this crankshaft. It spins on 4 special bearings. The bearings come split into 2 halves due to the shape of the crankshaft. BB must fit them securely into place.
The main crucial part about the split bearing is it has to stay together. We joke about it in saying that they're married. If they split and get divorced, it can be really messy.
It's crucial that BB positions the bearings correctly, or the crankshaft could shake the engine to pieces.
I'm gonna gauge the split bearings on the crankshaft to make sure that it's set in place. Once it's green, that means it's good to go.
The pistons and crankshaft are now ready to deliver the motor's 300 horsepower. The outboard motor powers this 1.7-ton boat through the water. But boats don't cruise in a straight line. They need a steering system too. As the steering wheel turns, an electric pump in the engine injects 150 cubic centimeters of hydraulic fluid at 2,000 pounds per square inch to the steering chamber. As the pressure builds, the fluid drives a corkscrew-shaped gear shaft up or down. The steering column rotates the motor up to 32 degrees in either direction to maneuver the boat safely, accurately, and with minimum effort. This outboard motor combines huge power with great handling. The motor provides the power while the lower unit delivers the hairpin turns. This motor is complete. But before it can leave the factory, Chris must push it to its limits.
We have the cage to protect ourselves in case there is a catastrophic failure with the motor. The motor could blow apart. We're here to check and make sure that that happens here and not out in the field with the customer.
Chris opens up the throttle and wraps up the revs. He listens for any unusual sounds.
We, as testers, get to know how a motor runs. We're listening for any sounds out of the ordinary, like a knock or grinding, rattling. This motor sounds and is running good to leave the factory.
Whether powering through the water or twisting out of a turn, innovative engineering and intelligent design work together to give the outboard motor a mighty punch. The pneumatic drill. How does this machine screw nuts tight and sand surfaces smooth using nothing but air? Under a toughened aluminium casing, over 40 parts work in unison. A high-pressure hose delivers air into the motor at 90 pounds per square inch and spins the blades at 18,000 times a minute. Exhaust air rushes out through the handle, where a steel wool muffler silences the sound. A spring-loaded quick-release chuck switches between drill bits in just a few seconds. Whether screwing or drilling, this machine can tackle some of the toughest jobs. The drill draws its power from compressed air to generate its ferocious speed. The secret to the motor's rapid spin is the way workers in this Missouri factory use precision engineering to build the drill's parts.
There's a number of things that could go wrong. Just constantly keep an eye on it.
Kevin operates the machine that carves out the drill's air motor. The part must be just the right size to spin freely without leaking air.
One of the most crucial measurements is the rotor body, the length of it. If it's out of tolerance by 1/1000th of an inch, you could either lose power or it could essentially lock up the motor.
Kevin checks the dimensions of the parts to make sure they will deliver maximum power.
Every 10th rotor that comes off the machine will go through a quality control process. Check the length of the body, and then also the diameters of the bearing journal.
This part is good to go. High-pressure air expands into the drill with explosive force. This is how the air makes the drill spin. At the heart of the drill is the reversible pneumatic motor. High-pressure air pushes against 4 blades. It spins the rotor at 18,000 times a minute. A set of 3 interlocking gears slow down the drive shaft and crank up its turning force. This way, you can tighten or loosen any nut in seconds. Workers assemble the gear package by hand to make sure that it can remove the most stubborn of nuts.
This is everything that provides the tool the power to be able to get the jobs done.
It's Sam's job to fix the drill's 3 gears onto the rotor.
We start with a spindle. We insert the gears onto the spindle pins.
The gears reduce the number of times the drill's drivetrain spins in a minute. Each turn of the drill bit now carries extra force.
These are the important part of the gear package. This is what takes the tool down from 18,000 RPM to 2,600 RPM and dramatically increases the torque.
The inner gears deliver monster turning forces directly to the drill bit. But all that twisting action is useless if the drill bit is the wrong shape for the job. So the bit must swap out in an instant. The inner casing that holds the drill bit has a steel ball lodged in its side. The ball locks against the spring-loaded outer sleeve when the bit pushes in. Underneath, a hexagonal joint stops the drill bit from slipping. One quick twist on the outer sleeve allows the ball to retract into a groove cut into its side, to release the bit in under a second. As the drill bit spins, the huge forces could easily scour through the motor casing. The secret to the motor casing's durability is the way that workers mount the drivetrain on bearings.
Building the motor. It's a bit fiddly with the vanes.
Justin positions the air rotor and its 4 vanes into a metal casing. Then he fits a bearing around the rotor's drive shaft so it spins straight.
If you don't have a bearing there, it's just going to cause a wobble in the motor, and your tool's not going to last more than a couple hours.
Justin must then lock a small pin on the motor casing into the drill's handle. The pin keeps the motor fixed in place as the air rushes through.
Actually, that was quite easy. It usually takes a couple times.
Justin screws the gear case tight onto the drill casing and tests every drill that leaves the factory.
So the final step is to test the tool, test the RPM. We always make sure that it sounds right. You have to find the sweet spot.
The tighter the gear case, the less air escapes from the motor and the faster the drill spins.
As you tighten it, as the pitch gets higher, the motor's spinning faster.
The drill delivers its maximum power at 2,600 RPM.
That's as good as it's going to get. Locked it down as tight as it could go. It's ready to roll.
The pneumatic drill delivers a hard turning action. It uses nothing but air to shift metal rusted on metal. The Ballpoint pen is an ingenious design. How does it manage to write clean, sharp lines without leaking ink all over the page? Inside a tough aluminium casing, 15 parts work together. A super hard 1mm tungsten carbide ball sits perfectly inside a precision-engineered socket, so the ink runs freely but doesn't leak. A hermetically sealed cartridge holds 3.4 grams of ink, enough to write 300,000 words, while a spring-loaded cam retracts the pen's nib in a split second. It's the perfect writing tool. The tungsten carbide ball must roll over the page without leaking ink. The pen's smudge-free lines depend on the way that workers in this Nevada factory put its nib together.
I've been here, I think 34 years, right in there.
Danny operates the machines that create the nibs. What Danny doesn't know about ballpoint pen nibs isn't worth knowing.
We take a coil of stainless steel wire, and then it gets fed into a rotating head with 2 carbide cutting tools on it. It comes out a solid blank. That's where we start the process.
Danny drops these short lengths of steel into an ingenious machine. It has 18 stations that transform the steel blank into a nib and position the pen's 1mm ball inside it.
There's just enough clearance between the ball and the socket for it to rotate. If we're not perfect, then they can't go out the door.
The pen can draw a clean, continuous line of ink. But how does the nib pop in and out with just a click of the thumb? When the pen clicks down, it pushes on 2 interlocking mechanical parts. As they slide down and push sideways, The bottom piece locks into a slot on the side casing and holds the nib in place. With the sentence complete, another click unlocks the cam and releases a tightly coiled spring which retracts the nib safely back inside. The pen's ink must flow freely to write smoothly on the page, but dry quickly so it doesn't smudge. The runniness of the ink hinges on the way that workers put the ink cartridge together.
I've pretty much worked in every department other than actually making the ink.
Caesar runs this factory's day-to-day operations. His #1 priority is to keep the ink flowing through this machine and into the pen's cartridges.
We can make like 15 to 20,000 refills a day. On a good day, about 25,000.
The cartridges move on a conveyor between the machine's 8 stations. The first station squirts ink in.
The most important thing about this machine is to have consistent pressure. That way all the ink gets pushed out and used up.
The machine slides home the ballpoint nib, squeezes in a dollop of glue, and seals the cartridge shut with a brass plug.
When the ink is cold, it's almost like a tar. It's very gooey and gummy. As the ballpoint turns, it turns it into a more liquidy substance.
The pen's ink becomes runny under pressure, so when the ballpoint nib presses down on it, the ink flows freely onto the paper. Caesar tests one nib in 25. These doodling machines check that the pen nibs roll smoothly and that the ink flows freely. To pass the test, the nibs must write non-stop for more than 3 kilometers. Only when they make the grade can they leave the factory floor. The ballpoint pen is an unsung invention, an intricate machine that keeps human civilization on track. The mighty outboard motor, the treadmill, the turntable, and the outdoor grill. What's inside isn't big, but it is clever. Next time you see one of these machines, remember, there's more to how things work than meets the eye.